Hearing will now come to order. Good afternoon and welcome to today's Research and Science Education Subcommittee hearing on 21st century biology. There are an increasing number of reports showing how cheap DNA sequencing and computing power, together with our growing ability to control molecules at the smallest scales, are driving us toward a revolution in biology. Some believe that if we can combine vastly increased amounts of data with increased collaborations between biologists, computer scientists, mathematicians, and engineers, we might be able to understand, manipulate, predict, or even design the most complex system there is, a living organism. Although biology was not my favorite subject in high school, although that may be because it was my first semester freshman year and we had to dissect the fetal pig, and I can still remember the smell of that formaldehyde, the new 21st century biology has me much more interested. I was trained as a mechanical engineer, and when I hear people talking about cells as a systems design problem, I understand the important role of engineers and physicists working in biology and how new biology may be able to deliver on promises to solve critical problems in fields like energy, the environment, manufacturing, and agriculture. This afternoon, we're going to take a closer look at the promise of 21st century biology by exploring research happenings at the intersection of biological sciences, the physical sciences, engineering, and mathematics, and its potential to address real-world problems. We'll also look at how these potential advances can be translated into technologies that benefit society, and what we need to do to train researchers who can thrive in an area that doesn't fit into any one department. For example, research at the intersection of biology and engineering, known as synthetic biology, which we will learn more about today from Dr. Leonard, could lead to the development of bacteria that could help clean up the oil spill in the Gulf of Mexico, produce cellulosic biofuels, or even lead to an organism that can detect and destroy cancer cells. The current market for synthetic biology-based products is estimated at $600 million, and it is expected to grow to over $3.5 billion within the next decade. This trend highlights the importance of today's hearing, the need to link research outcomes to American companies and American jobs. As a former university professor, I've seen firsthand the difficulty of overcoming cultural and institutional barriers between academic departments and schools. Even within a single discipline like political science, researchers often stay safely within their subspecialties. But the potential successes that can be realized by having interdisciplinary teams working on biological problems mean that we need to ensure these collaborations continue to grow. I'm interested in hearing recommendations from today's witnesses about how the National Science Foundation can foster interdisciplinary research and how it can improve education and training for students who want to work at the intersection of the biological sciences, engineering, and the physical sciences. Finally, I'd like to hear the panel's thoughts on the need to increase research coordination and collaboration in the biological sciences across the federal agencies. I thank the witnesses for being here this afternoon and look forward to their testimony. Chair now recognizes Dr. Ailish for an opening statement.
Thank you, Mr. Chairman, and thank you for having this hearing. It's a very important topic and, frankly, a very difficult topic. And I'll get into some details of that in just a moment. Let me also mention that I have, as often happens here, something else going on simultaneously, so I may be dashing in and out, but I will always be in earshot of what's going on here, so I'll keep track. The collaborations between the biological sciences, physical sciences, and engineering are becoming much more common at our major research institutions. Young investigators have discovered that to remain on the cutting edge of their research, they need to be partnering with various departments to solve challenges that are much larger than a single discipline. This type of research arrangement will inevitably benefit students by preparing them for today's workforce much more than an education bound by a single discipline. At the same time, we need to ensure that our graduate students do not become overly broad instead of gaining a great level of expertise in a disciplinary area. I can emphasize from some personal observations the difficulty of doing first-class, high-quality research in two different fields. I have a friend who has a Nobel Prize, not in biology, but decided some years ago that the future was in biology and related fields, and so transferred over. And even though he earned a Nobel Prize in one area of science, he has never, to the best of my knowledge, contributed significantly to the area that he entered into involving biological sciences. So I think it's very important for us to respect that fact, particularly as we discuss funding for the future. And it's not at all clear that funding decisions up to this point at the various funding institutions, in fact, show recognition of that, and how difficult it is, particularly for the older researchers, to switch from one field to another or try to combine two fields. I think this is clearly a case where we have to make certain that the young scientists coming along are early on recognized and given grants so that they can grow equally in both fields at the same time, instead of first mastering one and then attempting to master another. So I think that's probably the most important thing we can learn here in this committee, in that it relates to the funding and how to fund appropriately to ensure that the good scientists do have the money they need to accomplish success in two, maybe even three fields simultaneously. As this committee determines how to foster new models for science and engineering research, today's witnesses will provide valuable insights on both conducting research in the new biology and integrating it with other disciplines. I certainly look forward to hearing about this topic from our witnesses. I thank you for putting together a good panel, Mr. Chairman, and I'm sure we can learn a lot about the issues that I raised a moment ago from this distinguished panel we have before us today. With that, I yield back.
Thank you, Dr. Ailish, and I know this is a very busy time. I actually have two other hearings going on committees and subcommittees I'm on, so hopefully if you do have to go,
I will be in and out. So.
We will carry on without you. I wanted to point out an article in the New York Times just yesterday that calls attention to why we're holding this hearing today. The issue of new biology or 21st century biology is obviously our witnesses all understand it very well. The general public certainly does not have that great of an understanding of what all of this means. I can't say that I have, certainly I don't come close to what our witnesses know, knowledge that they have, but this article in New York Times provides an example of some of the exciting research that's happening at the intersection of biology and material sciences. An interdisciplinary team is converting methane to ethylene using genetically engineered viruses. Now, ethylene is used widely in industrial products and processes such as manufacturing of solvents, but the process of producing ethylene hasn't changed since the 19th century. The work of this group is a significant step toward a more sustainable and less expensive process. So clearly there are many things going on right now in new biology that will allow us to make great advances. And it's one of the reasons why that we are holding this hearing here today. So at this point, if there are members who wish to submit additional opening statements, their statements will be added to the record at this point of the record. So right now, I want to start by introducing our witnesses. First, we have Dr. Keith Yamamoto, who is chair of the National Academy of Sciences Board of Life Sciences, as well as professor of cellular and molecular pharmacology at the University of California, San Francisco. Dr. James Collins is the Virginia M. Ullman Professor of National History in the Environment in the Department of Ecology, Evolution and Environmental Science at Arizona State University. Dr. Reinhard Laubenbacher is a professor in both the Virginia Bioinformatics Institute and the Department of Mathematics at Virginia Tech. Dr. Joshua N. Leonard is an assistant professor in the Department of Chemical and Biological Engineering at Northwestern University. And Dr. Carl Sanford is the Vice President for Technology Development at Genencor. As our witnesses should know, you'll each have 5 minutes for your spoken testimony. Your written testimony will be included in the record for the hearing. When you all have completed your spoken testimony, we'll begin with questions. Each member will have 5 minutes to question the panel. So we will start with Dr. Yamamoto.
Thank you. Good afternoon, Chairman Lipinski and members of the subcommittee. I'm Keith Yamamoto, researcher, professor, executive vice dean of the School of Medicine at the University of California, San Francisco, and chairman of the Board on Life Sciences of the National Research Council. Thank you for the invitation to discuss with you today this report, the report from that board of the National Research Council called A New Biology for the 21st Century. The report was sponsored by the NSF, the NIH, the Department of Energy, and was co-chaired by MIT professor and Nobel laureate Philip Sharp and DuPont Senior Vice President Thomas Connolly. I also served as a member on that study committee. To begin to describe the new biology report, allow me to weave an imaginary scenario of research and science education for you in the Biology 101 classroom of a college or university in your district. So here's the professor. I'm good at this part. In this course, we're going to dig into the fundamental principles of biology, and you'll see that there are exciting mysteries waiting to be solved and within your reach. You'll also learn that more than ever before, deepening our basic knowledge could help solve major societal problems. For example, discoveries in biology could allow us to breed new food crops that thrive under terrible growth conditions and give each region of the United States a thriving biofuel industry with transportation fuels produced from locally and sustainably grown biomass. To achieve this, you'll need to team up with your classmates in physics, chemistry, engineering, math, computer science, to crack the deepest secrets of how living organisms obtain energy, grow, resist stress, combat disease, and dispose of waste. Getting there will require a focused effort to apply that understanding to invent new technologies. And of course, getting there will require your curiosity and excitement about biological discovery and its potential for profound social impact. The new Biology Committee proposed that this scenario become reality, that our current biological research enterprise, that remarkable discovery engine spread across more than 20 federal agencies, be augmented with a small number of 10-year challenges that are urgent and inspiring, but unreachable without a coordinated approach that aligns the separate strengths of multiple agencies. Why this approach and why now? Because many of the pieces are in place to make it work. The unity of biology means that knowledge gained about one genome, one cell, organism, ecosystem is useful in understanding many others. Physical scientists, mathematicians, and engineers are already entering this field and contributing unique approaches to biological puzzles. Scientists are exploiting the benefits of the Human Genome Project, new information and imaging technologies, and whole new fields such as synthetic biology. Nevertheless, the committee found that we are missing critical synergies and leveraging opportunities because the new biology is currently poorly recognized, inadequately supported, and delivering only a fraction of its potential. The committee recommended that the United States can better capitalize on emerging knowledge in the life sciences by coordinating efforts toward urgent societal challenges in 4 broad areas: food, energy, the environment, and health. Why go after these huge, sweeping issues? First, because we are in crisis mode with each. We must find ways to provide food and energy to a growing population without destroying our ecosystems. We must reduce the burden of chronic disease in our society and of malnutrition and infectious disease in the developing world. Second, because big goals, like putting a man on the moon or sequencing the human genome, can inspire both scientists and the public. Big goals can focus the imagination, creating the technological breakthroughs essential for achieving those goals. Finally, big goals provide accountability, a commitment to concrete, measurable results in return for sustained investment. The committee called for visionary scientists and engineers from the various focus areas to meet to identify some big goals, some great challenges. In March, new biology committee members briefed Department of Energy Secretary Stephen Chu, Department of Agriculture Secretary Tom Vilsack, and Howard Hughes Medical Institute President Robert Tijan, who then agreed to sponsor an early June workshop to generate challenge ideas that could provoke quantum leaps towards sustainable production of food and biofuels. The workshop brought together 30 extraordinary scientists and engineers who converged on a common overall goal: to sharply increase productivity in agriculture and biofuel production while simultaneously making both of those sectors carbon neutral. Clearly, neither USDA nor DOE alone can achieve this goal. Rather, a coordinated effort would be required, a national new biology initiative that harnesses the capabilities of these and other agencies. NSF, to stimulate necessary advances in fundamental knowledge of plants and ecosystems. NASA, NOAA, USGS, and NIST to work with DOE's Ameriflux program and NSF's NEON program to develop the ability to monitor carbon flows. NIH to contribute its expertise in genomics, basic cellular, molecular, and microbial biology and bioengineering. Finally, to return to the college classroom scenario that opened my testimony, a new biology initiative would demand reassessment of biology education. The committee strongly endorsed 3 major recommendations from the 2003 NRC report, Bio 2010. First, ensure that biology students are well-grounded in math, physical sciences, and engineering. Second, offer interdisciplinary, independent lab research experience as early as possible. And third, provide faculty development time to embrace the integration of biology with the physical sciences, math, and engineering, and to revise courses accordingly. The New Biology Initiative adds a new layer to the traditional strategies, marshaling basic science purposefully toward solving urgent societal dilemmas, focusing teams of researchers, technologies, and foundational sciences across agency boundaries. The initiative is a daring maneuver with great potential benefits: a more productive life sciences community, a better educated citizenry, a broad range of new bio-based industries, and most importantly, a science-based strategy to produce food and biofuels sustainably, monitor and restore ecosystems, and improve human health.
Thank you, Dr. Yamamoto. Dr. Collins.
Thank you very much, Chairman Lipinski, Ranking Member Ehlers, and committee members. I appreciate the opportunity to testify before you today on 21st century biology. It is a topic of vital importance to sustaining America's leadership in science and technology. The biological sciences will flourish in the 21st century by sustaining strength in its core disciplines while simultaneously supporting research at the intersection of the natural, physical, and social sciences, as well as engineering. Interdisciplinary methods cut across disciplines to combine in powerful ways basic research with solving real-world problems. Biology itself emerged as an interdisciplinary science late in the 19th century, when researchers studying physiology, natural history, anatomy, and other sciences argued for uniting them as the new discipline of biology focused on the study of life. Some late 19th and early 20th century life scientists also conceived of their research more within the realm of engineering. They thought that their studies should be focused on controlling life. They envisioned manipulating, transforming, and even replicating living systems in order to understand nature and also to help solve human problems. It's a 19th century perspective reminiscent of modern synthetic biology. Throughout the 20th century, the two great themes of understanding and controlling life wove together, even as biology divided itself into basic subdisciplines of genetics, cell biology, ecology, and evolution. Two things stand out as we look to biology's 21st century future. First, more and more research questions require reintegrating biology subdisciplines, and the fields are making some progress in carrying out that integration. The second thing we see is the biological sciences as a growing source of inspiration for and collaboration with engineering, the physical and social sciences. Computational biology, systems biology, and sustainability science are products of this merger. However, even as we imagine biology's role in addressing today's challenges, we cannot forget that these will change over time. This means that U.S. institutions that fund and conduct research must be innovative and adaptable. Reinforcing this need is the fact that many of the challenges ahead will not be solved by business as usual. Innovation must be the hallmark of research and education if a new biology envisioned in the recent NRC report is to be realized. Creating and sustaining an innovation ecosystem in the life sciences means that all the pieces must function as a system, which generally means lowering the barriers that block the ready flow of knowledge and ideas between, for example, academic departments, funding agencies, or the public and private sector. As we look at the history of science, it's also clear that the process of discovery changes. In an obvious sense, new tools and methods are developed, and that remains true today. But modern research also joins individuals into larger and larger teams. New methods like crowdsourcing and prediction markets are linking experts across the globe, effectively lowering those barriers I mentioned earlier. Funding agencies can also use these innovative methods to help find the very best research, and NSF, for example, is already using some of these methods. In a rapidly changing world, the process of discovery itself is also changing, and our students must learn how to keep up. Modern biology curricula should expose students to this sort of thinking and more. Because today's students are tomorrow's problem solvers, we must integrate research and education to prepare the next generation to address 21st century challenges. I urge this subcommittee in Congress to support innovative agency efforts to catalyze transformative research and education at levels that sustain reasonable success rates. Disciplinary and interdisciplinary programs that drive the ready exchange of knowledge and ideas. Efforts to advance curriculum reform in biology, and establishing appropriate metrics to judge programs. The subcommittee asked me to comment on university industry collaborations and coordination across U.S. federal agencies. These topics are related. Knowledge creation and use, along with the best ideas to identify and fund research and education, should not start or stop at the borders of one organization. In the best cases, the relationship between a university and an industry partner, or either of these with a federal funding agency, should be a two-way process of learning best practices from each other. Coordination across federal agencies builds coalitions and lowers barriers while leveraging the innovative ideas of several institutions. At the best, this really creates an open source environment for innovation. One last thought. In the NRC's new biology report, we see the central themes of biology's origins: understanding life, controlling life, and a call for broad engagement with other disciplines, recast in new forms around contemporary problems. Modern science, engineering, and technology are full of breathtaking discoveries. It would be wrong, however, to conclude that scientists and engineers can solve all the problems of food, health, energy, and the environment. Social scientists call these questions in these areas wicked problems for a reason. They're full of complex, interdependent parts, and solving one aspect of a problem often reveals or even creates other problems. Simply put, so-called wicked problems will not yield to only scientific or technological fixes. America's best researchers and their students must engage in a process of discovery that transforms the way in which research is conducted and students are educated. If the changes needed are to occur at a sufficiently fundamental level, it will also mean transforming our research institutions. I've envisioned a future for biology that has three elements. First, sustaining disciplines while blurring their boundaries. Second, innovation is a central feature of life science research and education. And third, building coalitions among institutions. In combination, these three elements are a vision for how the life sciences will play a key role in addressing the great intellectual and social challenges of the 21st century. At the same time, we will sustain America's leadership in science, engineering, and technology innovation during the years ahead. Once again, thank you, Mr. Chairman, for giving me the opportunity to testify on this very important subject. I would be pleased to answer any questions that you have.
Thank you, Dr. Collins. Dr. Bakr.
Good afternoon, Chairman Lipinski, Ranking Member Ailish, and members of the committee. Thank you for the invitation to testify today on 21st century biology. My name is Reinhard Laubenbacher, and I'm a professor at the Virginia Bioinformatics Institute at Virginia Tech. I'm also the Vice President for Science Policy for the Society for Industrial and Applied Mathematics, an organization with approximately 13,000 members who work in academia, government, and industry. While our members come from many different disciplines, we have a common interest in applying mathematics and computational science towards solving real-world problems. I will speak to 3 areas in my testimony today. First, research to address grand challenges. Second, fostering interdisciplinary collaborations and cross-agency coordination. And third, workforce development, education, and training. The first area I want to discuss is research to address the grand challenges. A central finding of the National Research Council report is that new information technologies and sciences will be essential to achieving the new biology for the 21st century and meeting challenges in health, food, energy, and environment. 2 examples of how mathematics can contribute to the new biology are first through modeling, the ability to describe the essence of complex biological systems with mathematical equations will allow researchers to test their understanding of a system and make predictions about how whole organisms and ecosystems behave. And secondly, through ways to deal with data. Mathematics provides techniques to access, analyze, visualize, and understand the ever-growing amounts of data generated in the life sciences, be it DNA sequence data or satellite surveillance data. My written testimony goes into more detail on specific research areas in mathematics that should be supported as part of the new biology. To support this research, an array of complementary federal programs will be needed, from those that focus on building expertise or enabling research networks in a single topic area, often at a single agency, to application-driven programs that cross agencies. The second area I want to address is fostering interdisciplinary collaborations and cross-agency coordination. The Virginia Bioinformatics Institute, where I work, is part of Virginia Tech's response to the challenge of fostering interdisciplinary research on its campus. I'm a mathematician by training, and at the Institute, my office neighbors are a statistical geneticist on one side and a biochemist on the other side. From our experience, it's clear to me that locating researchers with different areas of expertise under one roof can serve as an important accelerator of interdisciplinary research. Co-location allows researchers to develop a common culture and allows multiple disciplines to merge and organically develop together. The federal government should support this type of collaborations with programs that allow for co-location of disciplines by enabling new biological and new mathematical and computational research to be carried out within the same project. This way, the computational scientists developing algorithms, the engineers developing new technologies, and the biologists asking questions about the fundamental principles of life can advance the science in tandem. For this sort of interdisciplinary activity, federal programs that pool agency resources to allow the funding of larger scale projects are needed. The third and final area that I want to discuss is workforce training at several levels. In graduate education, both departmental and interdisciplinary PhD programs can be very effective in preparing students to conduct new biology research, with the key issues being an integration of curricula, the need for a balance between diversity and depth in training, as you mentioned, Mr. Chairman, and the opportunity to develop a common culture across disciplines. Federal support for efforts to align graduate education with these goals is needed, as creating and maintaining such programs requires a major investment of time and resources. At the undergraduate level, the 2 most important elements for preparing students to work in the areas of the new biology are again an integrated curriculum and research experiences. Close partnerships between teaching and research institutions can help in both areas. In addition, improved opportunities for faculty professional development, such as workshops that bring together faculty from diverse disciplines, will be critical. Finally, realizing the potential of the new biology will depend on future generations of scientists still to be nurtured. At VBI, we conduct outreach, in the Virginia Bioinformatics Institute, we conduct outreach programs that involve hundreds of children every year. I've seen the excitement on the face of a 9-year-old who, in a lecture hall with 400 other children, stands up and asks an insightful question after listening to a scientist talk about nanotechnology, a 9-year-old. Experiences such as this convince me that science in this country has a bright future. However, to get there, we all must engage in a joint effort to inspire and mentor the children who are the future of science. Again, thank you for giving me the opportunity to testify today. I've provided additional detail and recommendations in my written testimony, and I'm happy to answer any questions. Thank you.
Thank you, Dr. Laubenbacher. Dr. Leonard.
Mr. Chairman, thank you for this opportunity to discuss these important issues related to transformative shifts now occurring in research and education at the interface of biology, engineering, and the physical sciences. I am an assistant professor of chemical and biological engineering at Northwestern University, and my expertise and research interests center on engineering biological systems for applications in biotechnology and medicine using synthetic biology, a field that I will describe today. I'm honored to be here today and to speak with you in this subcommittee about these topics. Over the last 3 decades, molecular biology has revolutionized our ability to explore the living world, and we now stand at another transformative moment in the biological sciences. Through technological advances, it is possible to collect a wealth of biological data, and we now need new conceptual, computational, and experimental tools to transform this information into useful understanding and practical applications. Already it is clear that by developing these capabilities, we may use the richness of biology to meet pressing needs in areas including energy, through the sustained production of advanced biofuels, in the environment, including cleanup, remediation, and ecosystem management, agriculture, including crops that withstand harsh conditions or changing environmental conditions, materials, including the production of industrial useful materials like polymers from renewable biomass instead of from petroleum, in manufacturing, by carrying out chemical synthesis inside microorganisms to transform cheap biological feedstocks into high-value products like pharmaceuticals, and in health, by harnessing our own biology to treat cancer, to generate vaccines on demand, and to extend the quality of life. At the leading edge of these efforts is synthetic biology, a nascent technical discipline whose central goal is to transform biology into a system that can be engineered as we engineer mechanical and electrical systems today. Synthetic biology seeks a new paradigm of biology by design, in which one can conceive a desired biological function, design a biological system to perform this function, build the system, and have it work as predicted. We are still some distance from realizing this goal, but synthetic biology provides a framework for proceeding. In this model, basic biological parts, such as genes, are constructed and characterized such that they can be interconnected and assembled into novel configurations to generate new functions, which are designed with the assistance of computational tools and rigorous quantitative methods. As in all areas of applied science, construction and understanding are connected. First, we build to learn how to design. Understanding the principles of aeronautics did not directly provide the Wright brothers with the ability to achieve controlled flight. This was achieved only through an ongoing cycle of design, construction, testing, and refinement, and the same is true for engineering biological systems. We also build to understand. Sometimes understanding comes through failure. For example, through unsuccessful attempts to engineer a bacterium to perform a simple task, for example, turning a gene on and off in a regular fashion, we learned that cells do not function as well-oiled machines, but rather their inner workings proceed through bursts of activity. In these ways, synthetic biology is intrinsically part of the new biology of the 21st century described by the National Research Council. Synthetic biology is not a change within biology, engineering, or the physical sciences, but rather it is an effort that must span traditional disciplinary boundaries and integrate these strengths. Work in synthetic biology also spans the funding and oversight priorities of our federal agencies. At this stage, the basic challenges, technologies, and frontiers are largely independent of whether the eventual application is in energy, health, or the environment. For example, my research group works to engineer cell-based devices and networks, approaches that have applications in both biotechnology and medicine. Interagency cooperation is therefore required to make the best use of our collective capabilities and resources. The NSF has supported early synthetic biology efforts through the Multi-Institutional Center, SynBIRC. Now, we must also develop interdisciplinary centers throughout our research infrastructure to build a national synthetic biology community that is integrated with other facets of 21st century biology. Given the early state of synthetic biology and its vast potential for benefiting society, investing in high-risk, high-reward projects should form a major part of our national strategy. In 2008, the NSF conducted such an experiment, along with partners in the United Kingdom, by running a sandpit event that brought together a multinational group of researchers to foster innovation in synthetic biology and develop competitive projects targeted at grand challenges. For example, our team is building a technology inspired by the evolution of bacterial ecosystems that could transform our ability to construct complex functions in bacteria, such as the challenging biochemical synthesis of the anti-cancer drug Taxol. The National Academy's Keck Futures Initiative also held a synthetic biology conference in 2009, using interdisciplinary teams to develop field-wide perspectives on major scientific and ethical issues. These findings also generated several innovative projects. For example, our team is developing a technology to enable engineered symbiotic bacteria, which might patrol the colon for signs of cancer, for example, to communicate this information to their hosts. Finally, addressing challenges in 21st century biology requires training a new generation of students prepared to integrate diverse areas of expertise. At the graduate level in particular, we need to engage a broad pool of students and move towards models in which training is an interdepartmental effort, a strategy that we are developing and implementing at Northwestern. Nationwide, our students are already eager to apply their capabilities to meet today's pressing challenges. With the United States' adaptable and entrepreneurial cultures in both research institutions and the private sector, we are positioned to continue to lead this revolution in biology and biotechnology. By fostering a national synthetic biology community and investing in high-risk, high-reward research, we can capitalize upon our capabilities to realize the benefits of biology by design. Mr. Chairman, thank you again for this opportunity to share my perspective on this important topic, and I would be happy to address any questions you may have.
Thank you, Dr. Leonard. Dr. Sanford.
Good afternoon. My name is Carl Sanford. I'm Vice President of Technology Development for Genencor, and I'm honored to present this testimony to your committee. Genencor, a division of Danisco, is a leader in industrial biotechnology innovation and manufacturing on a global scale. We have multiple manufacturing, R&D, and sales locations throughout the world, with a central location in Palo Alto, California, and offices and manufacturing plants in Cedar Rapids, Iowa, Beloit, Wisconsin, and Rochester, New York. Our goal is to push the boundaries of what is achievable in the realm of biotechnology and accelerate development of the bio-based economy. This opportunity for my testimony comes at an exciting time for Genencor. Recently, we have made some exciting new advances in making isoprene from renewable feedstocks that promises to help our nation increase its technological competitiveness and decrease its dependency on imported foreign oil, while also protecting the environment. Genencor started in 1982 as a spin-out company from pharmaceutical biotechnology pioneer Genentech, with an aspiration of bringing to industrial and everyday customers the benefits of recombinant DNA technology through new product features and manufacturing efficiencies. Over the past 28 years, we have roughly doubled our revenues every 5 years, such that our business now approaches $1 billion annually. Our manufacturing processes are based on the conversion of biorenewable feedstocks like corn and soy into bioproducts like enzymes using efficient large-scale fermentation processes. Every day you eat, use, or wear something made with Genencor enzymes. Collaboration is a key for success. The rate of improvement in the seminal technologies of DNA synthesis, DNA sequencing, and synthetic biology is continuing to provide accelerating innovation opportunities. No single enterprise can go it alone, and hence the need for developing effective networks that connect the players. As an example, we are an industrial member of SynBERC, the Synthetic Biology Engineering Research Center, which is an NSF-funded multi-institution research effort establishing a foundation for the emerging field of synthetic biology. SynBERC's vision is to catalyze biology as an engineering discipline by developing foundational understanding and technologies to allow researchers to design and build standardized, integrated biological systems to accomplish many particular tasks. In essence, SynBERC is making biology easier to engineer. It is also engaged in training students who can leverage the investments and training as they go forward into industry. Powerful new technologies such as synthetic biology must also include governance and oversight to fully understand any potential unintended consequences. Hence, centers such as SynBERC also provide initiatives in which ethics and biosafety approaches are purposely incorporated into synthetic biology research and development. The collaborative human practices model within an NSF-funded SynBERC project was the first initiative in which social scientists were explicitly integrated into the synthetic biology research program. Increasing the science and technology acumen of our society and engaging young minds in science and engineering are key success factors for improving our innovation potential and social receptivity for technology-based solutions. ScienceBound, Iowa State University's premier pre-college program, prepares and empowers Iowan ethnic minority students to earn college degrees and pursue careers in science. In its 20th year, ScienceBound has worked with more than 800 middle and high school student and students and offered college scholarships to 200 program graduates. The program asked 12 and 13-year-olds to make a 5-year commitment. Working in tandem with expert teachers, students can emerge academically equipped as well as socially and culturally empowered to earn a college degree in science or engineering. We need to further support and expand this concept of making science fun and exciting and the learning process friendly enough to encourage commitment to a career in technology. Biotechnology and technology in general are played on an international stage. U.S. centricity is insufficient in providing the education and training necessary to be among the best, brightest, and most successful. Language skills, cultural receptivity, and global perspectives are requirements for biotechnology players of the future. International awareness is an area for improvement in U.S. education and training. The President's Innovation and Technology Advisory Committee, PTAC, has identified a technological congruence that is called the Golden Triangle. Each side of the Golden Triangle represents one of the 3 areas of research that together are transforming the technology landscape today: information technology, biotechnology, and nanotechnology. Each of these research fields has the potential to enable a wealth of innovative advances in medicine, energy production, national security, agriculture, manufacturing, and sustainable environments, advances that can in turn help to create jobs in the nation and increase the nation's gross domestic product. In combination, these fields have an even greater potential to transform society. This interplay of technologies, along with the ever more demanding societal needs, which creates grand challenges. Industrial biotechnology is one of the tributary themes to this Golden Triangle. Continued investment in research, education, business, and legal developments is necessary to achieve our collective aspiration of meeting the needs of the present without compromising the ability of future generations to meet their needs. Interdisciplinary collaborations that work the Golden Triangle in different patterns of innovation may offer routes to success, provided the membership, results, and ownership outcomes are based on transparency, trust, and database decision-making.
Dr. Sanford, I'm going to ask you to conclude as quickly as you can.
I thank the committee for the opportunity to present these views and welcome any questions and comments.
Great. Thank you, Dr. Sanford. I apologize for the interruption. The beepers or noises you've heard are the call to a vote. We have about 15 minutes. We're Pavlovian here. We begin to salivate when we hear those. And thank you to all the witnesses for the testimony. Dr. Lipinski departed so that he can vote and then come back. And our goal will be to try to keep the hearing going rather than have a prolonged interruption while we go and name sports or congratulate sport teams and name post offices. I want to thank the witnesses for their, believe it or not, for their expertise and their input. I'll recognize myself for 5 minutes, followed by Dr. Ailish. I'm intrigued by this concept and excited by it. As I get it, basically the idea is that we're going to, the new biology refers to the integration, sort of cross-disciplinary integration of lots of other fields: physics, chemistry, computational technologies, engineering. And the report suggests that one of the ways we develop this cross-disciplinary new biology is to apply it to kind of grand challenges, and that all makes good sense to me. So my question is, we've got NRC makes this report. Distinguished folks like you folks seem to be behind it. The biological section of NSF already receives a lot of money, $767 million request for the next year. What's going to happen? Do you think, and maybe Dr. Collins, this is appropriate to ask you, Dr. Laubenbacher, you seem to be working in an area where actually you're applying this, as many of you do, but what happens to NSF now? Do they look at this NRC report and say, by golly, these folks are right, let's start focusing our research funding on this, or do they keep in the same kind of channels they may have been in?
So, Congressman, NSF played a role actually in calling for the report. We were one of the agencies that were involved in it. And in fact, we've already started to marshal resources. I shouldn't say we, since I'm no longer with NSF, but the foundation has already started to marshal resources along these lines. Some of the things I referred to actually in terms of these new ways to look at interdisciplinarity. NSF has hired program officers jointly between directorates, for example. The sandpit process that Dr. Leonard referred to was one that we called for.
Give us a 15-second summary of a sandpit other than children playing in sand. With 5-year-olds, my mind goes there.
So the sandpit is in fact the sandbox, but it's out of the United Kingdom. That's where we got it. So your image is exactly the right image. We posted a question in synthetic biology, give us your best ideas. 170 two-page applications came in. Front page, what's your idea? Back page, a series of questions prepared by an industrial psychologist. How well do you play in groups, for example? Interest in interdisciplinarity. A committee chose 30 of those individuals, and they were all brought here just outside Washington, D.C. for a week, put together with program officers for real-time review of their questions, and groups were put together and matched within that week-long period. And at the end of it, we got 5 to 8 exciting proposals, some funded by the UK, some funded by the NS.
So get some really bright people who work well together, get them together and set them loose.
Set them loose.
Neat.
And it was a really creative way, the sand pit, sandbox, however you want to think about it, and we picked this edgy, innovative area, emerging, stuff is rough, that's right at the edges, and synthetic biology was the first place that we went to, for all the reasons that are in the report.
Gotcha. So NSF's already working on this. As they're selecting their new person to replace your position,
Right.
That person presumably will be savvy to this integrated issue. The other directors of other NSF programs are also on board?
They are. So when we decided to do this area of synthetic biology in the sand pit, engineering came on board very quickly. And then as the other directorates heard about it, all of a sudden we had the social sciences in, we had education and human resources, math and physical sciences. At the end of the day, all the groups had a piece of it.
Great. How will this affect grant applications, and how does it affect your training? You know, when I used to chair at a psychology department, I had this fun idea that we would just put all these disciplines, faculty members in a hat, and we would draw another discipline out. So I might draw a nursing faculty or a chemistry faculty or PE, and all kinds of neat things would come. All the other faculty freaked out. They said, oh, we can't do that.
Right.
Seemed to me pretty exciting. But how's it affecting your educational enterprise in preparing the students who will feed this new biology effort?
So look, I think the real challenge is to get students to be comfortable going into that sort of arena. Faculty members, as I suggested in here, have to get much more comfortable with lowering the barriers, much the way they are often in industry, where folks can move around much more easily.
Any others wish to comment on that? I've only got about 40 seconds left, so Dr. Laubenbacher.
Yes, I think in terms of training, it reminds me a little bit of the 1990s when we introduced calculators into teaching calculus. It's difficult to teach an old dog new tricks, as they say, and the students were far ahead of the professors at that time. And I think similar things will happen here, that students, as they grow up, if they're provided with the right environment, they will be way ahead in terms of interdisciplinary thinking.
Great, thank you. I'm going to recognize, thanks to all your answers. I have to be brief, so I recognize Dr. Ailish for 5 minutes.
Your questions were so brilliant, Dr. Baird, that they leave me wordless. So if you have a wish to pursue yours any further, go ahead. I just want to say I found this very enlightening, and I've got to wrap my mind around it a bit more. But I really, what you're doing is wonderful, and it's what I would love to do if I could return to science today. It's just so exciting to hear this again, and it brings back the memories of how exciting science was when I first encountered it, and I would love to join you.
I do have a follow-up, and both Dr. Ailish and I are going to retire. Maybe, Vern, we should go back in and both of us sign up and take this coursework if our aging brains could. But see, they will come up with a device that will allow our aging brains to comprehend what they're doing.
Speak for yourself.
Oh, okay, sorry. On a more serious note, though, so training, I'm very intrigued by this issue of how we train people for this, because it's already a pretty challenging thing to get a PhD in biology. Now you've got to somehow be able to interface with physics, chemistry. I mean, there's already a certain base level of awareness, et cetera, but are we going to need a longer amount of time in the training process, or is there just a new way of sort of wrapping one's head around the multidisciplinary approach? And I open that to everybody, but Dr. Yamamoto and maybe Dr. Sanford, you can talk about how you're doing this in your applied realm.
Well, let me begin and say that I'm hopeful that not only will we not require more time for the training, but will require less. The training periods in biology have gotten to be very extended to the point that investigators don't really begin their independent work until in their 40s and may have passed or at least lost some of the kind of age in which they're doing their boldest thinking and their boldest research. So hopefully the amount of time can come down. So the question then, of course, is a very good one, and that is how can this happen? And I would say that there are two ways to think about this. One is that we need increasingly to be thinking about working in teams. That increasingly we will have scientific endeavors that are carried out by groups of people who don't share the same expertise, but have enough familiarity that they know the kinds of tools that are needed, the kinds of experiments that need to be done, even though they themselves may not know how to do
So
them.
it seemed to me that needs to, not to pat myself on the back, but that model I had of
Your
working
model-
at a very early undergraduate age, where you're just really used to saying, okay, so I'm a social science major, but this semester I'm taking a course with physics students. That needs to happen very, very early on, so it's integrated into who you are.
Your model is exactly right. And so that in the teaching of biology, we need to be integrating some of these physical principles that weren't really needed before. We've passed through an era in which biology was mostly descriptive. We were trying to identify all the characters, see what they look like in the microscope, for example. And we've now advanced to a point where we really need to understand in a quantitative way how these things interact. And we're moving on to being able to require the physical principles, the mathematical manipulations to be able to understand what these things are. And students can track that and understand it early on and be able to integrate that learning. And so it'll be teams and a broader education from the outset, exactly as you said.
I've got to run and vote, as probably does Dr. Ailish. Dr. Lipinski resumed the chair. I apologize, I won't be here to hear the answer. Any quick comment before I go?
Yes, I would emphasize the word teams, building interdisciplinary teams where the team has a composition of the expertise required to solve the problem. And a problem is very important to help focus the attention of the team members on working together.
Thank you.
Well, the chair will now recognize himself. I guess I will have the opportunity now to ask my questions and conclude the hearing. I ran out there to vote to make sure that we could have this time to conclude the hearing rather than have you sit here probably waiting 45 minutes at least for us to finish with our votes and give the opportunity for those members to ask questions. A couple things that I wanted to ask, and I'll keep watching. As soon as this vote ends, I'm going to have to run out of here quickly, finish up here, dismiss you, and run out. But a couple of questions. First, a broad question, mainly for Dr. Sanford and Dr. Leonard, but for anyone else who has any, wants to offer any views on this. How does the U.S. position in synthetic biology compare to other nations? If we have an edge, what are our primary obstacles to keeping that edge? Dr. Sanford, why don't you start?
Yes, my view is that the U.S. is number one in the world in terms of leading the this thrust around synthetic biology, even defining the term and integrating the disciplines that are required to make synthetic biology work. Having said that, I think there's broad participation around the world, and frankly, there's much more eagerness that I see in the part of students and numbers of students in other parts of the world that I think the United States needs to really make the science and engineering, math, and technology a number one agenda for bringing students into this field versus transaction specialists.
Dr. Leonard?
I guess I can comment on an aspect that's related to sort of the previous question as well, which has to do with the undergraduate synthetic biology competition called IGEM. So this is an international competition, and over the 5 years that it's been around, it's been seeing increasing international participation. And the teams that participate from outside of the U.S. are strong in taking the top prize several years now going. So there is a groundswell outside the U.S. as well in interest in this area. So I would just second Dr. Sanford's comment that in my experience, it's still a hotbed of activity, and probably the majority of the driving laboratories are currently in the United States, although there is potential for competition and growth all over the world.
Any other witnesses have any comments on this?
Well, I think in terms of sustaining our edge, it really does go to comments that were made by all of us, and that is whatever can be done to facilitate the open sharing of knowledge between different groups, whether it's within departments in terms of universities or across our federal funding agencies. It's this openness that really is going to be important as far as powering something like synthetic biology, where at any time you do need the basic biological information reinforced by physicists, by engineers, mathematicians, and it's that culture, that environment of innovation, that however we can continue fostering that is going to be central to keeping the edge in terms of synthetic biology.
Dr. Yamamoto.
The new biology report suggests that by enunciating these major challenge areas, it will generate the technologies that we need to be able to achieve, to respond, to answer the questions. So, and this was really the case when the decision was made to put a man on the moon. The decision was made to sequence the human genome. In neither of those cases, at the time that the challenges were enunciated, were the technologies available to actually achieve the goals. And it was by enunciating the challenge and capturing the imagination of scientists about the ways that they could contribute to these challenges that those technologies became generated. And the impact of those being able to achieve those challenges has been immeasurable. There's an article in Nature magazine today about the impact of sequencing the human genome that goes well beyond being able to know the order of the nucleotides in the genome. And so there's a long way of saying that I think that the capacity for the U.S. to maintain a lead in synthetic biology or any of these other areas could actually hinge on the decision by our government or by ourselves to enunciate these kinds of challenges, capture the imagination of scientists as well as the public at large in ways that they can contribute. And that will certainly include this new exciting field of synthetic biology that really has a play, as we heard, in each of these areas.
Well, following up a little bit on that, if a new biology research initiative were created by the federal government, what should be done to ensure that the private sector is actively engaged and that the resulting research discoveries are translated to the marketplace? Whoever wants to start. Dr. Sanford?
One of the very important elements of working with universities from a GenNCORE standpoint is access and a window into new technologies. And I'd use SINBRG as an example of such a consortium of not only universities but companies that can participate and exchange ideas and learn together. Offer also students training in the companies where we use internships, for instance, in the summer to host some of the SINBRG students. And this is a great way to get dialogue and the exchange of information of developers of the technology and the users of the technology. Second, I think we have an opportunity to make the legal system a little bit more responsive and easier to negotiate in terms of licensing technologies from the universities into companies.
Dr. Yamamoto, did you want to add something?
Yeah, I think that one of the other key elements of the new biology report was the whole notion of cooperation between agencies that are supporting life sciences research. And we've entered one of the ways to think about the exciting era of biology that we've now entered is that we have in place we have all the cards on the table. And you play a different card game when you know that all the cards are on the table. And that's really where we are now. And having reached that, we can enunciate challenges that go from the most fundamental sort of question to the capacity to apply them. And I think the way that the government could play in being able to contribute to this is to be able to make funds available that will really bring together these sectors. So one of the things that the new biology report talks about in particular is different agencies within the federal government, over 20 of them, as you know, that are supporting life sciences research, being motivated by funding to be able to be working together. Funds available, for example, only for projects that require the expertise of 2 or more federal agencies. Exactly the same sort of scheme could be used for bringing together the public and private sector and in putting together exciting new decadal level challenge ideas that can be accomplished only through application of fundamental research that takes place within academia and its development and application in the private sector.
Dr. Collins.
In my written testimony, I alluded to an article in this Sunday's New York Times on these proof of concept centers that are being tried at a variety of universities now that have to do with funding ideas very early in the stream as far as getting them transferred into technology is concerned. Our funding agencies could play a role there. That's a policy decision as far as the government is concerned, where federal money should be used in crossing this so-called valley of death between an idea and getting it into technology. But there's also a place as far as basic research organizations like the NSF is concerned for funding individuals who want to study this entire process of moving from idea into technology. Upstream, how do you get it started? And downstream, what are the conditions under which it's successful or not successful? And what can we learn from both of those sorts of things? So it seems to me there's a variety of places where this could be thought through, both in terms of injecting funds, but also studying the process itself and how it works.
Thank you. Dr. Laubenbacher.
I think synthetic biology is a real poster child for the kind of research that the National Academies report advocates, and I think everything that the members of this witness panel have talked about apply to it. And in particular, as Dr. Leonard mentioned, the IGEM competition is an incredibly good tool to get students excited. We have one of those. We field a team at our institute, and it's been terrific to watch. In terms of making sure that the fruits of basic research get turned into products that actually help society. I think that, again, synthetic biology and in other areas, for example, I'm a bit familiar with research done by pharmaceutical companies. As basic research becomes very important, I think there'll be more opportunities for research collaborations between companies and academics that do not involve IP issues, and intellectual properties is in many cases the stumbling block between successful, for successful collaborations.
All right, thank you. One very quick, and if I can get an answer quickly from Dr. Sanford, and maybe you want to follow up in a written form. How well do you think the current regulatory guidelines apply to synthetic genomics? Do we need a different set of guidelines for synthetic genomics relative to natural genomics?
Yes, I do. I think that's true. We do need additional guidelines with regard to synthetic biology. One example is that in the regulatory terminology, there's no such thing as a chassis. What is used as host strain would be another terminology. So when a synthetic biology company brings forward to the regulatory experts terminologies that they're not familiar with and that really don't have a track record, at probably the very least, the regulatory trail is now complicated and lengthened. So I think there's an opportunity here to get ahead of the wave, so to speak, and do some definitions and some exchange of information with regulatory experts to get advice on how to do this without undue problems.
Well, thank you for being quick there. And if any other anything else you want to add, I'd appreciate a follow-up in writing if there's anything else you want to add to that answer. But I want to thank all the witnesses today for their testimony. The record will remain open for 2 weeks for additional statements from the members and for answers to any follow-up questions the committee may ask of the witnesses. It was I think, a very good hearing, and we had, despite all the competition, we had a good turnout of members, and I expect there will be some follow-up questions to this. And with that, the witnesses are excused, and the hearing is now adjourned.